So our next speaker is Brandon English and from Red Rocks College, and he's going to talk about academic and industrial applications of Benchtop NMR in Colorado. So take it away.
All right, good afternoon, everybody. So I'm going to be giving a talk today about academic and industrial applications of Benchtop NMR. I am a full-time faculty member at a community college here in Lakewood, Colorado. We're just west of Denver. And we've been working together with the folks over at Q Magnetics, specifically John Frost, for a while now on our applications of NMR here. And you just got to see what was inside of that box, and I'm in the last talk, and I'm essentially going to talk about what we're using that box for in this academic environment, as well as with some of our industrial partners. I think John Price was being a little bit modest when he said, when he was talking about the QM125 doing one thing well. I think at the end of this talk, you'll get the vibe that we're really doing a lot of things with this. Chiefly allowing access to our constituencies here at the community college. So our main mission at a community college is access to all of our citizens to education. We happen to be kind of a quirky community college in that we have folks anywhere from GED level all the way up through our master's degree. We are regularly graduating physician's assistants out of our programs here. We are multi-site as well. So we are a pretty STEM heavy school. So just want you to be aware of where we're at the moment. So the chief applications that we have here at Red Rocks are second year organic chemistry. That's an obvious one. I am an organic chemist. I'm actually a natural product synthetic chemist and a medicinal chemist by background. So I'm actually going to leave a lot of the technical questions up to the QMags folks. Which just kind of goes to show you how versatile this platform really is if you can get one of these synthetic guys like me to work with this, it's pretty easy to use. So we're using this for synthesis characterization in our academic laboratories as well as reaction monitoring. One of our major mandates lately has been supporting transfer to the chemical engineering programs at some of our four-year partners. And so reaction monitoring is pretty critical for those folks for their basic education. We've also applied the instrument to our introductory and general chemistry laboratories. NMR is very rarely taught in introductory and general chemistry laboratories, but I really needed to be able to justify having multiple benchtop instruments at the college, and only serving our organic chemistry classes was probably not going to be viable for that. So we applied also, there's very little hands-on quantum mechanics teaching that you can do in these courses. Pedagogically, it was very nice to have real-world active learning demonstrators. And that's really what I've been using the Benchtop NMRs in our classrooms for. So we introduce quantum mechanics and essentially show that this is an application of quantum mechanics in a chemistry laboratory, as well as isotopic ratio determination. So that's a classic general chemistry lab, is determining the isotopic ratios. I'll show you how we're doing that with our benchtop instruments. And then the last thing I'm going to talk about is our workforce training. It's another major mission of the community colleges, is to reach out to industry partners and make sure that we are training students for our associate's programs, as well as some of our bachelor's programs, so that they can easily move into industry and they can easily take skills, real world skills into that. And so I'll show you some of the characterization work that we've been working with the QMags folks with, as well as some of the contaminant analysis for some of our partners in the cannabis industry. This is Colorado, right? So if we're talking natural products in 2024, cannabis is pretty hot right now. So major industry with a lot of growth potential. So this is a slide of quinine spectrum. I'm showing this. This is what students would see as a walk-up instrument once they gathered quinine. Pretty complicated structure, and the beauty of this is that I don't really have to worry, like I did with previous instruments, about limiting structure to my students. A major learning goal of organic chemistry, as most of you probably remember, is being able to read spectra and essentially map protons onto some kind of a structure. The beauty of this UI for this instrument is that there's very few things that an undergraduate can break. Undergraduates, I say that now, and now I'm thinking about all the ways they have broken it, but they will find every possible way to break an instrument, especially if it's software involved. And so this piece of QI is nice because, or sorry, UI is nice because there's a little fewer options. I can, of course, expand this out. So I can expand out for the essentially what we're calling expert mode. And if I do have advanced students, or if I have, or myself, or any of our lab techs that are capable of more training, we're able to have a lot more sort of tweakability to this instrument. So I'm going to go back a slide here. This is what a student would see, much more straightforward from a learning environment. And then there is a capability of going in there and adjusting from there. So one of the classic experiments in sophomore organic lab is total synthesis. And the learning objectives of a total synthesis are first, analyzing your starting materials for purity. Second, executing that total synthesis. And we try to focus mainly most of our syntheses on natural products. That's partly due to my background as a natural products chemist, as well as the industrial applications of this. The second major learning objective is measuring to see if the reaction is complete or not, and understanding the kinetics and thermodynamics of that reaction. And then finally, analyzing the crude product as well as the purified product in the end. So this synthesis has been in the literature, the chemical education literature, for decades, and we make heavy use of it. It's the synthesis of isoamyl acetate. This is the active flavor and smell compound in bananas. So if you have that characteristic banana smell, this is also a product of an awful lot of yeast fermentation. So that's pretty critical to the brewing industry, which is another major industry in Colorado at the moment, is this specific compound. So the students take isoamyl alcohol, and you can see a beautiful spectrum from the QMag 125 here for isoamyl alcohol, and they can get their starting material purity as well as just mapping these protons onto that, essentially teaching all of the fundamentals of reading a proton NMR. And they're gathering these spectra themselves. Before the benchtop NMRs really started coming online, 2010, 2012, we would have had to ship all of our students to one of our four-year partners. For us, that was usually the Colorado School of Mines. That involved an entire day, a field trip, signed permission slips, and just a nightmare of logistics. Now I can have a handful of instruments that the students can walk up to, and they can actually have the freedom to fail with this instrument. And by freedom to fail, I mean they're gathering their own spectra, and I can just sort of stand there over their shoulder and allow them to do that. So beautiful spectrum here of the starting material. After reflux and acetic acid for about an hour and a half, we end up with isoamyl acetate. And so here's another QM125 spectrum of isoamyl acetate. Noticing that we can inject this directly, right? This is these can be injected as neat samples. So for liquid samples, there is zero sample prep, which is another beautiful thing because we don't have to buy expensive deuterated solvents. We don't even have to do solvent mixing or anything. We can have direct injection. And our students can inject this. This is the distillate. Another cool part about this lab is the final step of this is distillation of the final product. So we can inject a crude spectrum. I didn't have any crude spectra at hand because my students immediately did distillation this time around. But this is the final product of that distillation. So they can actually even monitor that distillation process by just literally syringing directly out of their flask at different times and just injecting directly onto the instrument, which is pretty nice. Another thing I like about the Teflon tubes in here is more or less they're very robust. Again, students will break everything. They're a very robust system for injection. So that's a pretty classic introductory organic chemistry 1 lab. We can then teach the students about further analysis by doing overlays and talking about why these protons are shifted. So obviously these are the protons here. This triplet represents the protons that are shifting to the left here. They're shifting what I call left field, or what my students call left field, because we're trying to get that across. And we can talk about why that's occurring, the physics behind that, as well as the electron density of this acetyl group and what exactly it is doing, as well as we can see the loss of the exchangeable proton here from the alcohol and the gain of the acetyl singlet on this methyl group. So I don't need to teach any of you about this. I'm sure you all understand it, but this is revolutionary when we're talking to an undergraduate, for them to actually see these shifts occurring, because a major learning objective is, what is the electron density around this proton? How does this functional group, this ester functional group, change that relative to this hydroxyl functional group? And the hands-on ability is absolutely, to use the instrument is absolutely critical. We can then break this out even further. So by talking about coupling constants, so you can see these J trees that are shown in here, break those out and do full analysis of coupling constants. Something that we wouldn't be able to do with previous benchtop instruments. We just didn't have the resolution with the previous instruments. The new 125 has enough resolution that this is very easy to do, and I can actually introduce this concept to the hands-on lab as well. I've been trying to strive quite a bit in my career to step back as an instructor. The old model of the sage on the stage, giant lecture hall organic chemistry instructor who is just yelling facts at their students, is fading away rapidly, especially with the diverse group of students that we have at the community college, and the hands-on project-based learning is growing massively. This instrument allows project-based learning because it is walk-up and it is very low maintenance. Another very important thing to these laboratories is I don't need to do a ton of prep ahead of time. I essentially shim the magnet the day of the experiments. The students run through it at the entire day, and then we clean up at the end. It's not like I have to hold hands throughout the entire thing. I also don't need to maintain liquid helium or liquid nitrogen for a cryogenic instrument. But very quick anecdote about when I purchased my very first Benchtop NMR. I put in the purchase order and I went to get a final signature on it. And my dean said, I'm really concerned about this nuclear magnetic resonance machine that you're buying. I want to make sure that we have a lead-lined room, and I want to make sure that it has several locks on it. Because I don't want the radiation from your instrument interfering with the other students in the room. So the beauty of this is that I could literally take this instrument down to his office and wave a Geiger counter in front of it to prove to him that we were not shooting off any alpha particles into the environment. So moving on. So another major advantage to the flow injection ports on the 125 is that we can do continuous reaction monitoring. For the introductory chemistry and the organic chemistry 1, this isn't really critical, but for when we get into organic chemistry 2, as well as when we're training chemical engineers, understanding equilibrium concentrations, understanding reaction monitoring, and understanding essentially the kinetic and thermodynamic calculations that we'll be doing in physical organic chemistry is pretty critical, and this allows for this. So this reaction here is the Fischer esterification of benzoic acid in acidic methanol. So we have a Bronsted acid catalyzed Fischer esterification. So the initial product of this is, of course, methyl benzoate. Methyl benzoate shows up beautifully on an NMR, and if I were to simply rotovap the product down, I would get exclusively methyl benzoate. A large portion of the learning objectives in organic chemistry 2 is acetal chemistry and carbonyl chemistry, and understanding the reaction mechanism of this. And students don't get to see the full mechanism. And involved in that mechanism is this metastable orthoester that occurs when methanol is used as a solvent under acidic conditions. So this orthoester is not normally visible because the sample prep would involve rotovapping down our material, and then that would Le Chatelier this back to the methyl ester, and we would exclusively isolate this. Being able to visualize this by NMR is critical for the students really trusting in the mechanisms that we're showing on this. So here's the reaction running here. It doesn't even need to be stirred. You can see the pump in the background. The pump's doing the bulk of the stirring. So this is continuously sampling that, injecting it into the 125, and then re-injecting it into there so we can gather samples NMR of the crude reaction mixture, not even a crude reaction mixture, just the actual reaction mixture the entire time. So here's the data on this that you can gather. Many thanks to John Frost at QMag for helping gather all of this data for us. But this is fantastically exciting for a mechanistic nerd like myself. So here are the scans. And then here's a graph of the proton concentration that we have here. So we're going to be using these meta protons in all three of the species. So starting material, the orthoester and the methyl ester, that's going to be essentially our background here. So if we're going to keep this constant, that's going to allow us to essentially normalize the other curves against this. And you can see a buildup in, first of all, total methyl ester. Sorry, this is a buildup in total OCH3 protons. So that would be the methyl groups in all three of the methyl groups on the orthoester, as well as the methyl group on the methyl ester. So this is the total. We see buildup of the methyl ester as we sort of move through, and we see buildup and steady state concentration of that orthoester. And these equilibria arrows are critical to student understanding. Students that leave general chemistry tend to think chemical reactions occur in a irreversible pathway, essentially moving forward only and then never reversing. It's critical to establish that understanding of steady state concentrations, especially when we're talking about reaction mechanisms in the later part of Orgo 2 and in our biochemistry areas. So the buildup of that is absolutely beautiful. So this is our total product buildup, and then that essentially is a sum of these two that are occurring here. I absolutely love this. As you can tell in the excitement in my voice, this is really causing a breakthrough in how we think about teaching these ideas. So, and then in our general chemistry area, not only do we get to show results of NMR, and we get to talk about, spin states and that sort of thing as an application of quantum mechanics, which is about the first third of general chemistry nowadays. We get to see that that's actually occurring in the laboratory, but the students in a general chemistry lab or an introductory chemistry lab get to run their own experiments. They get to run their own experiments, and they get to apply that to not just the quantum side of things, but they also get to apply that to the isotopic ratios. That's another major learning objective. So we can measure the boron 11, boron 10 isotopic ratio with sodium tetrafluoroborate. Sodium tetrafluoroborate, we're going to assume that we have a natural abundance of boron 11 and boron 10. And of course, because of the spin state differences between boron 11 and boron 10, boron 11, 3 halves spin state, and a 3 spin state for boron 10, we're going to get a different coupling with the fluorine 19, the spin 1/2 nucleus at fluorine 19. This gets us an entire day of lecture just talking about what these spin states really mean. And we can gather this pretty quickly using fluorine 19 NMR on the exact same instrument we've been gathering proton on. So for the introductory chemists, we don't want to burden them with an awful lot of analytical work. We more or less want to we want them to gather their spectrum, and we want to hand them a procedure for getting at their data. And I'll tell you right away, they're not terribly patient group of folks. So Integration of these peaks for introductory chemistry, we keep that mostly to, well, let's integrate the entire thing and let's integrate just the boron 10 signal, which you can see back here. So just to orient everybody, there's a quartet here that's due to the boron 11 fluorine coupling, and there's a septet hidden behind here that is a boron 10 to boron fluorine, or sorry, to fluorine 19 coupling there. So we can integrate the entire thing. And for students, that's as simple as clicking here on MNOVA to integrate just the peaks above this line. So the sensitivity of that integration, we can automatically gather that data, and then we can click much further down and gather the entire data. So we're going to get a 1 to 1.22 integration ratio, which 1/1.22 ends up giving you a boron 10 percentage at about 18.1, which is really close to the accepted range that's there. And that allows us to sort of move into that discussion academically. For the more advanced students where we're trying to teach better data acquisition skills, we can do a more careful analysis. So I tend to do this for more honor students or for folks that are looking for just a deeper understanding or a deeper interest in the material. So this would be less of our life sciences folks, less of our PA nursing folks, and more of our, again, honor students, chemical engineers, those sort of folks. They can go in, and if they want to individually integrate each of these different peaks, and of course that septet is hidden behind there, so we can talk about the data analysis involved. We can only see 5 of these peaks of the septet. So I asked the students the question, exactly how would you analyze this if 2 of your peaks are obscured? And we get proposals in, and they can come in and say, okay, I'm going to integrate these 5 peaks. I'm going to divide that and we'll do the fraction, blah, blah, blah. And they can get an actual error bars on this analysis. So they come out to 18.935%. And again, that's a lot closer to that range with a ludicrously good sensitivity, at least that's what we tell them, ludicrously good sensitivity, which is even better for those sort of more advanced students. Now, to give you an idea, as far as our student population, organic chemistry 1 and 2, we will generally have something like 75 to 100 students a year at our Lakewood campus. But general chemistry will have much closer to 300 or 400 students. General introductory chemistry will have even more of those. So the access that a benchtop instrument allows is pretty critical. I will tell you flat out, we would not have access to NMR for the vast majority of these underserved student population if it weren't for the benchtop instruments that we have. We would not have a cryogenic and high field instrument on campus. That is not even close to reasonable, given our budget constraints and given our overall mission. So I've shown you the organic side, and I've shown you the general and introductory chemistry side. Next, we're going to look at some of our industry partners. So special thanks goes out to John Frost and Community College of Denver's Cannabis Science program. The program over there is teaching cannabis science, major industry in Colorado nowadays, around the hemp side of things. So we have to be very careful legally with Schedule I materials. The beauty of the ins and outs of the legal system in the United States are that Schedule I materials do not include hemp. So anything that is hemp derived is perfectly fine for us in Colorado to handle, as well as our industry partners can ship hemp products to other states. So you may have heard of D8, which is Delta 8 THC. This is very popular, especially in the South of the United States, as an industrial product, because this is not regulated the same way marijuana is regulated, because it is a hemp-derived compound. And this can also be chemically modified once it's derived from hemp. So we have up here THCA. So this is the THCA sample. The difference between THC, which is the classic psychoactive compound in marijuana, and THCA is this carboxylic acid here. I'm going to show you a slide on the conversion of THCA into THC here in a little bit. But here's our THCA. You can even see the carboxylic acid proton there. So we can characterize this compound as pretty readily, as well as measure for gross purity of the compound. Other popular compounds in this space in Colorado have for production are HHC. So this has become increasingly popular in the hemp space because it's not called THC. So you'll notice that THCA has this unsaturation here. That's delta 9 unsaturation. This would be delta 8 unsaturation. This is a fully saturated ring. So what that does legally is allows the cannabis folks to no longer call this THC. This is HHC. This has many of the same psychoactive effects as THC without the legal encumbrance of it being THC. So this is a very popular product. And you can see, that's a HHO, that should be HHC. You can see that fully throughout this, again, characterization as well as purity determination of HHC. Delta H THC, there is a classic problem in the distillation of delta H THC, which is contamination with what we're calling Smurf blood, and you'll get a vibe for why we're calling it Smurf blood once I show you that. But we can get contaminated oxidized version versus contaminated unoxidized version in the same the same sample. And again, I'll show you that in a future slide. We'd also look at the acetylated versions of this. So a lot of these are for bioavailability as well as legalistic reasons why we're interested in these analogs of THC, which again is not legal in a lot of circumstances. So this is the conversion of THCA to THC. So an exciting reason to use THCA is that it is not regulated as a Schedule I narcotic or Schedule I drug, but it is very readily converted just through the use of heat into THC. So if this were heated up and inhaled in a vape cartridge or anything like that, that conversion is readily happens, and we need to make sure that we're monitoring the kinetics of this. So we can monitor pure THC's conversion, or pure THCA's conversion into THC by loss of the carboxylic acid proton that's here, obviously, and growth in that aromatic proton through here. So you can pretty readily measure that, the kinetics of that step, as well as if you want to just make sure that you are not doing this before shipment. You want to make sure that you're getting pure THCA. If you're shipping this to a more regulated market, that's going to be pretty important. And then this is just a close-up of the same thing. So we see growth in this aromatic proton here in THC versus the total THC concentration in these two peaks here. So that would be THC plus THCA because of course those peaks overlap with each other. Here's our Smurf blood. So obviously this is why we're calling it Smurf blood. It turns blue. So during distillation of D8 or delta 8 THC, some of the other terpenes that are present in the natural samples will produce azulenes. And these azulenes are not only brightly colored, which is extremely problematic for shipment of these as a industrial product, but they're not well studied. And so we obviously don't want medical products going out with azulenes present. And so you can see these azulenes here versus these weakly acidic species coming in on this side. So a lot of our students are headed into this space, and being able to make these measurements is pretty critical, and actually allowing the students to hands-on make these measurements, as well as the ability to either use these in a solvent or as a neat sample if need be, or if that's convenient. So I want to thank everybody for listening to me. Also, especially all my thanks go out to John Frost over at CCD, as well as at QMAG and the folks at QMAG for all their support in this and help gathering spectra and coaching on all of that, and for putting up with me as as a synthetic chemist here, and then Murphy Murray for providing the THCA samples for us. And I'll take any questions that you have from there.
So questions?
I've just got a comment about the fluoroborate experiment. The sodium borohydride experiment was published in 2005, and that experiment was actually fully resolving all the boron 10 and boron 11 peaks. And so for students, it's a great experiment because it's the only experiment I can think of that you can demonstrate why atomic mass is not integral. So it's a great experiment and it can be done very quickly and easily.